Alright there, junior physicists. I'm making this video to help you understand a little bit more about a hugely important part of kinematics and the next unit that we call mechanics. Okay? It is the four motion equations. Okay? I call them the Fab Four because these things are huge. They're very important to a study of physics. And it starts from all the things that we've talked about so far. All right, so understand that we started with an understanding that we said, based off of the idea of slope, that the average velocity is displacement over time. Okay, so we've been talking about that a little bit, so let me throw that up here. Average velocity is displacement over time. Now, yes, ooh, that's very blurry. Come on, focus. There we go. All right. So, when we talk about an average, think about math. Let's say we know that the car starts at a certain speed, and then we know what it ends at. And assume that whatever going on between is relatively consistent. Okay? Now, this is really getting funky out there. I guess when I move, this camera doesn't like it. Anyway, so if you had two speeds and you want to find the average, just like two grades and you want to find the average, you add them up, divide by 2, okay? So what we're going to talk about is, instead of saying the average like this from now on, we're going to talk about the average in terms of an initial velocity and a final velocity. And to average them, we're going to add them up, divide by 2. So that is our first big equation. Okay. Now, we also talked about that the slope of a velocity time graph is acceleration. So that means that acceleration is based off of the slope. Well, the slope is the rise over the run. The rise is the vertical column. Well, that would be the change in y, or in our case, the change in velocity. Delta is a symbol we use to say change in velocity over change in time. Okay, well, I'm not big on the whole delta t thing. A change in time just means an amount of time. All right, so we're going to rewrite this one a little bit and say, well, that means that a equals change in velocity. A change means that we're taking the difference between the final and the initial. So I'm using the same variables that we did here, okay? And then instead of delta t, I'm just going to call it t. Okay, well, that second equation is usually written as VF equals VI plus AT. Okay, that's just rewriting this. If I multiply both sides by T, I'd get the T out of here, so that's where AT comes from, and then I bring that VI to the other side. Okay, so that's where the second big equation comes from. The third and fourth come from doing substitution, combining them to form something else. Okay. I don't know that you want me to go through all of that. I'll make a separate little video explaining how you combine them to do that. Okay, but for example, since I know VF equals VI plus AT, I could substitute all that in for VF here. And when I do that, and I rearrange the whole thing, and it's a whole process of rearranging, I would get my third equation that we say D equals V initial T plus 1/2 A times T squared. Yeah, I know, it looks like a lot, but I'm going to simplify it as we go along, so bear with me. All right, and if I had substituted in instead for time, taking either one of these, I could get a fourth version of the equation that VF squared equals VI squared plus 2 times A times D. So there are our Fab Four. Those are our kinematics equations, okay? And I know that doesn't mean squat to you yet, but that's okay. One step at a time. All right, so if you look at the worksheet on Fab 4, you'll see that these equations are there right at the top of the paper. They're on the equation sheet that you should have by now anyway, so I'm not asking you to memorize them, but let's break it down and talk about what they mean and just make a little table of this so that you're a little bit clear about the whole thing. All right, so I'm going to rewrite these all on the side over here. F equals VI plus AT d equals vi times t plus 1/2 times a times t squared. Vf squared equals vi squared plus 2 times a times d. Okay. So in total, we see that there are 5 variables. So we have vi, vf, d, t, and a. The order, of course, does not matter. Vi stands for the initial velocity. Okay? Meaning at the start, whatever it says at the beginning of the problem, at the beginning of the scenario, at the very start, how fast is it going? Okay? Vf means final velocity. So that's what's going on at the end of the situation, the problem, the example. D represents displacement. T represents the time. And A represents the acceleration. So what if there is no acceleration? We've talked about some scenarios already where there wasn't. Well, then A is 0. And if A is 0, Vf equals Vi. Well, if there's no acceleration, the final initial speed should be the same because it's not changing its speed. And if I put a 0 in here, I end up that d equals v initial times t. Well, we kind of saw that in our equation because if I take d divided by t, I expect to have v. So we've seen all this before. It's no big deal. If there's no acceleration, it does not change anything. Think about, this here, the average velocity equals distance over time. Well, if the speed isn't changing, then the average is constant. Whatever 2 speeds, let's say the speed is 6 meters per second. 6 plus 6 is 12, divided by 2 is 6. We're still getting 6 either way because it's constant. So this is good regardless of whether there's acceleration or not. All right, let's talk units. We've been doing that a bit lately. For velocities, we expect the unit to be meters per second. For displacement, we expect it to be meters per time seconds. Acceleration gets a little confusing to some students, okay? Because acceleration is based off velocity divided by time. It's meters per second per second. Now, there are people that write it as meters per second, okay? I don't, okay? I find that confusing, okay? We write it as meters per second squared. Now, you might be wondering how I get from this to this, so let me rewrite it a different way. So let's say we have meters per second, and I'm dividing by second. Well, in math, you should have learned that when you divide by a number, it's the same thing as multiplying by the reciprocal. And so I end up with meters over second squared, which is what acceleration is. Okay. So we're going to go into this whole problem-solving thing. And again, I'm going to emphasize the I guess method here, or the guess method, if you will. The I in I guess usually means making an illustration. You might need to picture this a little bit. I'm not going to emphasize the picture part too much, but the rest of it, showing, understanding it, what's in there. That's the physics. All right, so we're going to just take a look at a few of these questions real quick and talk about that. So let me just switch screens real quick. Okay, so here we see our Fab 4 up top on the paper and our first question. So we're told that John starts from rest, then boarded down a slope which is 435 meters long. It takes him 2 minutes. What was his acceleration during this time? All right, so what we need to do is to be able to focus on the givens, okay? In every problem, there has to be 3 givens. Has to be. All right, so we might have to do a little interpretation of some things, but let's start with the obvious things. We see that it says that John boarded down a slope which is 435 meters long, okay? So we know the displacement is 435 meters. And I know you probably can't see my board. I'll switch screens in a minute. So I know D is 435 meters. We're told the time is 2 minutes, which again, we know we have to convert to seconds. So I'm going to multiply that by 60 and say that's 120 seconds. Okay. What's the third piece of information? Well, we were told that he starts from rest. If I'm at rest, what does that say about my motion? I'm not moving, which means that my initial velocity is 0. Okay, so that's a key thing you have to pull out of there. That word, rest, will come up a lot. When we say it starts from rest, we're saying the initial velocity is 0. So that little bit of interpretation is important. And of course, we're looking for an acceleration. All right, so let me shift my views again now, back to here. You can see the givens, the unknown. All right, now we have to decide on equation. All right, so here's the thing about this Fab 4 stuff. Okay, every equation has 4 variables. There's a total of 5 things, though, right? We said VI, VF, A, D, and T. So that's 5 variables. But every equation only has 4, and every problem has 4. So it's just a matter of figuring out which equation is the right one. Now, we could just try and match up the letters, or what some people will teach you to do is look for the one that's not there. So we have VI, we have A, D, and T. The only one that's not there is VF. So I need the equation that does not have VF in it. And that happens to be this one here. We see D, VI, T, and A in it, but there is no VF. Well, we have D, VI, T, and A. That's our problem. There's our equation. So there's the physics, okay, of figuring out which equation we're dealing with, okay? Then from there, we're going to just do some substitution and solving. So I'm going to substitute in for D, 435 meters. VI is 0. The time is 120 seconds. Well, what's 0 times anything? 0. So that part doesn't matter. Plus 1/2 times A times T, 120 seconds squared. Don't lose your squares in these equations. Very, very important. All right, so now I have to do a bit of multiplying here. Well, first I'm going to square this. So let's take it step by step. 435 equals. I'm going to ignore this since it's all 0 and say we have 1/2 times A times 120 seconds squared. So 120 squared, it's something like 14,000. Yeah, 14,400 seconds squared. Now you don't have to put your units in, but I wanted to make sure you understood something about this, so I'm going through. Now, what I'm going to do, since this is all multiplication, I'm going to take 1/2 of 14,400 and get 7,200 seconds squared times A. Now I'm going to divide both sides by 7,200 seconds squared, and the reason why I want to emphasize that is that, all right, this side cancels out. Notice I'm going to have units here of meters per second squared. That's where the units come for acceleration. So I didn't just make that up before. You could see that if you went through, the units would be there. Okay, so now I'm just going to do the calculation. So 435 divided by 7,200. And my acceleration is 0.06. So A equals 0.06 meters per second squared. Now, I don't know the direction other than to say down the slope, okay? So we want to try and put directions in when we can. This problem was limited, but that does give some specificity to where John was going. All right, let's shift views back and talk about the graph. Okay, so now it's asking us to make a graph of what's going on in this problem. Okay, so we're going to have to assume that the velocities are positive. We know we have a positive acceleration. So when we talk about making our graph, like we did in the previous assignment, okay, I know that because it's accelerating, there has to be a curve. I know I'm starting at a rest, so that means my slope has to be flat to start, and it's got to be building up. So we should have a graph that looks something like this. I'm not looking for specifics. I just want to make sure you understand what the shape of the graph should be. So that should be the shape of John's graph. All right, let's go on to number 2. Now it's Lauren's turn. Lauren was gliding along at 25 meters per second before slowing down to 10 meters per second over 52.5 meters. What was Lauren's acceleration? All right, so we look at it, we see 25 meters per second. That's going to be the initial velocity because that's what came first, right, at the start of the problem. And the 10 meters per second, got interrupted there. The 10 meters per second is got to be the second or final velocity. And then we have 52.5 meters. That's got to be a displacement. And finally, we're asked what is her acceleration. All right, so now that I've got my stuff written, and it should views here back. All right, so you see I have VI, VF, D, and A. Okay, and now we just got to decide on which equation. Now notice what's not there is time. So if an equation has time in it, I can't use it. So the only equation I can use is the one without time. So I'm going to choose that equation, VF squared equals VI squared plus 2 times A times D. Substitute in for VF is 10. And again, I understand if you leave off the units, okay? I probably will start doing that soon, but I'm just trying to be a little extra thorough right now. 2 times A times D, 52.5 meters. All right, so let's do some simplification. 10 squared is 100. 25 squared is 625. And 2 times 52.5 is 105. Okay. Now this is where a lot of people will make mistakes. Keep in mind, I can't add these numbers, okay? They have different units on them. This has an unknown. Can't do that, okay? So that's part of why I have put the units in there. Okay, but these two things have the same units. So I can now subtract 625 minus 625 from these. Here I'm going to get negative 525. That's going to cancel out, and I'm going to be left with 105 meters times A. So now I'm going to divide both sides by 105 meters. Okay, this meter is going to cancel out with one of those, so now it's just meters per second squared. Hey, we got those units for acceleration again. Cool. All right, so now I take negative 525, divide by 105, and I'm going to get negative 5 meters per second squared equals A. A negative is implying we're going in the opposite direction. So it is giving us direction in a way, because whatever direction they're going in, I know that's in the opposite direction. So you will see negatives in these. A negative acceleration, some people call it deceleration. That's not true all the time, but it would be true here. It's slowing down. Deceleration usually implies that something is slowing down, okay? But there are scenarios there where a negative acceleration just means speeding up in the wrong direction. Okay, in the opposite direction. All right, so before we go into the graph, let's talk about our speeds. Our speeds are positive, but our acceleration is negative. Okay, so again, I know that we're starting with a curve, okay, and I know that I started with a higher speed and went towards a lower speed. So that means that my curve has got to start steep and start getting shallower. So we get a curve like this. So this would be a positive velocity, negative acceleration graph. All right. Let's shift on and go to number 3. How much time is required? All right. So right off the bat here, I know we're looking for T. Is required for Maddie's car moving at 48 meters per second. Let's call that VI. to come to a stop. All right, we talked about the word rest before. What does the word stop mean? If I stop, well, my speed is 0. So that means the final velocity has got to be 0 because we already had the initial velocity. If the car's acceleration is -6 meters per second squared. So again, that negative is implying that it's accelerating in the opposite direction. That's what's causing it to slow down or decelerate, if you will. All right, so I have my information. Let me shift my screen. All right, so we have VI, we have VF, we have A, we're looking for T. All right, so that means we're going to go with this equation right here. Notice there's no D in this equation, there's no D's here. It all works out. So VF equals VI plus AT. VF, which is 0, equals VI, which is 48 meters per second, plus A, which is -6 meters per second squared, times T. All right. I'm going to move this over to this side. So I'm going to subtract 48, subtract 48. So this is -48 meters per second equals -6 meters per second squared times time. So I'm going to divide both sides by -6. Okay, so -48 divided by -6 is 8. Meters per second divided by meters per second squared. You can see the meters will cancel out, the seconds will cancel out, but not one of them. We're going to have 8 seconds as our time. All right, so there is the process. Now let's just talk about the graph. We have positive velocity and a negative acceleration. That means it's the same graph as the last time. Okay, we're starting with a big velocity. This time I know we're going to 0, and 0 means it's got to be flat. So we have a graph that looks like that. All right, let's do the next one together, shall we? Number 4, the speedometer on Ethan's motorcycle was not working initially. Ethan throttled it up for 600 meters. Okay, so that sounds like a displacement to me because it's in meters. Over the next 15 seconds, that sounds like a time to me. And then the speedometer started working and told him his speed was now 216 kilometers per hour. Oh, that's just ugly. All right, so we're going to have to do a little conversion there. And the question now is, what was Ethan's initial speed? So if you thought that 216 was the initial, the question then would be kind of moot, right? We know that he was going something, but he couldn't read the speedometer. But at the end of the problem, he could read it. So 216 is his final, and we're looking for his initial. All right, so let me come back up to here. All right, so let's review those conversions real quick. So 216 kilometers per hour. Okay, 1 kilometer is 1,000 meters. And I like to do the hours right into seconds, so I'm going to say 1 hour is 3,600 seconds. Hours cancels out, kilometers cancels out. I've now got meters per second. So I'm going to take 216 times 1,000, divide by 3,600, and I get 60 meters per second. All right, so I have VI, D, T, and VF. Notice that there is no A in this equation. Well, the only equation that doesn't have an A in it is that first one we worked with. So that's the one we're busting out now. VI plus VF over 2 equals D over T. VI we don't know, but VF we do know is 60 meters per second. We do know the displacement is 600 meters. We know the time is 15 seconds. All right. Let's simplify this side first because that's an easy side to simplify. Okay, so 600 divided by 15 is 40. So I'm going to rewrite this as VI plus 60 meters per second over 2 equals 40 meters per second. Now to get rid of the fraction, I'm going to multiply both sides by 2. So that cancels out. And so now, if you don't mind my writing up here, I have VI plus 60 meters per second, and 2 times 40, of course, is 80 meters per second. Now I subtract 60 from both sides, and I find that VI was 20 meters per second. All right. Now, we don't know the acceleration, but I do know the speed started at 20 and is going to end at 60. So the speed is increasing. It has a positive acceleration. All right, so we're looking at a situation where we have positive velocities and a positive acceleration. And so that means we were to look at our graph, we're looking at something like that. Okay, maybe not exactly, but again, the general shape is there. That's all that matters. All right, I'm going to stop there. That's numbers 1, 2, 3, and 4 done for you. You now do 5 and 6 for homework and post it to Canvas. All right, I hope that helped. I'll talk to you soon. Bye.